The winter of 1943 brought more than just snow to the Eastern Front. It brought a mystery that would challenge everything Soviet engineers thought they knew about German engineering superiority. In a cramped metallurgical laboratory in Moscow, far from the frozen battlefields where tanks clashed in brutal combat, a team of Soviet scientists was about to make a discovery that would fundamentally alter their understanding of the enemy they faced. The story begins not in a laboratory, but on a battlefield near Kursk, where the largest tank battle in history had just concluded. Soviet recovery teams were working through the wreckage, cataloging destroyed vehicles, salvaging what could be reused, and most importantly, gathering intelligence. Among the twisted metal and shattered dreams of the German offensive lay something particularly valuable: intact sections of armor from the fearsome Panther tank. The Panther, or Panzerkampfwagen 5, had earned a terrifying reputation among Soviet tank crews. Its sloped armor seemed to deflect shells that would penetrate other tanks. Its long 75mm gun could destroy a T-34 from distances that seemed almost impossible. When Panthers appeared on the battlefield, Soviet tankers knew they were facing something different, something more dangerous than the earlier German tanks they had learned to fight. Soviet High Command wanted answers. How thick was this armor really? What made it so effective? Could Soviet guns defeat it? And most importantly, could Soviet industry replicate it? The samples were rushed to Moscow, to facilities where the Soviet Union's best metallurgists worked around the clock analyzing enemy equipment. These were not ordinary scientists. They were experts who had learned their trade in the harsh school of total war, where every discovery could mean the difference between victory and defeat, between life and the alternative. The lead metallurgist assigned to the project was a man named Sergei Makonin. Before the war, he had worked on railroad construction. Now he led a team responsible for understanding the very best of German tank metallurgy. Makonin and his colleagues approached the Panther armor samples with a mixture of professional curiosity and personal determination. Many of them had lost friends or family to German tanks. This was more than just science. It was personal. The first tests were straightforward. Measure the thickness, document the angles, calculate the effective armor values when accounting for slope. The numbers were impressive, but not shocking. The frontal armor was 80 millimeters thick, sloped at 55 degrees. This gave it an effective thickness of about 140 millimeters against a straight-on shot. The side armor was much thinner, 40 to 50 millimeters, but still respectable. These measurements confirmed what Soviet tank crews already knew. The Panther was a formidable opponent, but Makonin wanted to dig deeper, literally. His team began preparing samples for microscopic analysis. They cut through the armor plate, polished the cross-sections, applied acid etching to reveal the internal structure of the steel. This was where the real secrets would be found. The grain structure of the steel, the presence of alloying elements, the heat treatment methods, all of these would tell a story about how the Germans had achieved such impressive results. What they found initially seemed to confirm German superiority. The steel showed a careful, deliberate structure. The heat treatment had been expertly done, creating a hard face that would resist penetration while maintaining enough toughness in the backing to prevent shattering. The alloy composition included nickel, molybdenum, and chromium, elements that significantly improved the steel's properties. This was high-quality armor steel, the product of an advanced industrial nation with deep metallurgical expertise. Makonin's team documented everything meticulously. They measured hardness values across the armor plate. They performed impact tests on small samples. They analyzed the chemical composition using spectroscopy. Every test confirmed what they expected. This was world-class armor steel, probably the best tank armor being produced by any nation at that point in the war. The report they prepared praised German metallurgical achievement, even as it grimly noted the challenge this posed for Soviet forces. But then something unusual happened. In early 1944, more Panther samples arrived in Moscow. These came from tanks knocked out during the winter offensive, several months after the Kursk samples. Standard procedure dictated that they be tested just like the earlier samples. After all, confirmation was important. But when McConnell's team began their analysis, they immediately noticed something was different. The first clue came during the hardness tests. The new samples were softer. Not dramatically so, but measurably, significantly softer than the Kursk Panthers. McConnell ran the tests again, thinking perhaps there was an error. But the results were consistent. These armor plates had lower hardness values across the board. That was strange. Why would the Germans be producing inferior armor for their best tank? The microscopic analysis revealed even more puzzling details. The grain structure was less refined, suggesting the heat treatment process had been different, perhaps rushed or done at incorrect temperatures. More troubling still, the chemical analysis showed significant differences in alloy content. The nickel content was much lower. The molybdenum was nearly absent. These were not minor variations. These were substantial changes to the fundamental composition of the steel. At first, McConnell and his colleagues were confused. Perhaps these samples came from a different manufacturer. German tank production was distributed across multiple factories. Maybe quality control varied between facilities. But as more samples arrived throughout 1944 and into 1945, a pattern emerged that could not be explained by simple manufacturing variation. The quality of Panther armor was declining, and it was declining rapidly. By mid-1944, Panthers recovered from destroyed tanks showed armor that was brittle and prone to cracking. Some plates showed evidence of poor welding with seams that could split under stress. The later samples were still thick, still sloped at the same angles, but the material itself was fundamentally inferior to the early production models. It was as if the Germans were building Panthers from increasingly worse steel, maintaining only the outward appearance of their earlier success. The Soviet metallurgists realized they had stumbled onto something far more significant than just manufacturing data. They were witnessing, in cross-sections of steel, the slow collapse of the German war economy. But to understand what they were seeing, we need to step back and look at the bigger picture of how the Panther came to be and what Germany was facing as the war progressed. The Panther's development had been driven by desperation. When German forces first encountered the Soviet T-34 in 1941, it was a shock. The T-34 combined sloped armor, a powerful gun, and good mobility in a way that German tanks of the time could not match. German tank crews, who had rolled through Poland and France with relative ease, suddenly found themselves outmatched. The standard Panzer III and IV tanks could not reliably penetrate the T-34's frontal armor, while the Soviet tank could destroy German vehicles from ranges that were previously considered safe. German High Command responded by ordering the development of a new medium tank that could counter the T-34. The project was given highest priority. Germany's best tank designers worked frantically to create a vehicle that could restore German armored superiority. The result was the Panther. It borrowed design concepts from the T-34, particularly the sloped armor, but executed them with German precision engineering and superior metallurgy. When the first Panthers rolled off the production line in early 1943, they represented the cutting edge of tank design. Every aspect had been carefully considered. The armor was made from face-hardened steel that combined a hard outer layer to break up shells with a tough inner core to prevent catastrophic failure. The sloping increased effective thickness without adding weight. The gun was powerful enough to penetrate any Allied tank at combat ranges. On paper and in early combat, the Panther was everything Germany needed. But there was a problem, a fundamental problem that would eventually doom not just the Panther, but Germany's entire war effort. The recipe for that high-quality armor steel required rare alloying elements, particularly nickel and molybdenum. Before the war, Germany had imported these materials from around the world. Swedish iron ore provided the base material. Nickel came from mines in Finland and Norway. Molybdenum was sourced from various international suppliers. Chrome came from Turkey and other neutral nations. As the war dragged on, Germany's access to these materials became increasingly restricted. The Allied blockade tightened. Supplier nations either stopped shipping to Germany or were no longer accessible. Conquered territories that might have provided raw materials were lost as Soviet forces pushed westward and Allied forces advanced from the south and west. By late 1943, Germany was facing critical shortages of the very elements that made their armor steel superior. German metallurgists faced an impossible dilemma. They could not stop producing Panthers. The tank was desperately needed on multiple fronts. Soviet numerical superiority meant Germany needed every Panther they could build. The Western Allies were now fighting in Italy and would soon invade France. Stopping production was not an option. But they also could not maintain the original armor specifications because the materials simply were not available in sufficient quantities. The solution, such as it was, came in the form of ersatz, substitute formulations. German engineers began developing armor steel recipes that used less of the rare elements and more of what was available. Nickel content was reduced from 2% to 1%, then to 0.5%, then eliminated almost entirely in late production vehicles. Molybdenum, which improved the steel's response to heat treatment and increased toughness, was similarly reduced or replaced with less effective substitutes. To compensate for the inferior alloy composition, German metallurgists adjusted their heat treatment processes. They tried different quenching methods, varied the tempering temperatures, experimented with alternative hardening techniques. Some of these adjustments helped, some did not. The result was armor that looked the same from the outside, that had the same thickness and slope, but that was fundamentally weaker at the material level. There was another problem too, one that made the situation even worse. Producing armor plate required not just the right materials, but also the right equipment and expertise. The process of making high-quality armor involved massive industrial infrastructure, blast furnaces, rolling mills, heat treatment facilities, quality control laboratories. This infrastructure required skilled workers who understood the subtle art of steelmaking. It required consistent electrical power for the furnaces. It required transportation networks to move raw materials and finished plates. By 1944, Allied bombing campaigns were systematically destroying German industrial capacity. Rail lines were cut repeatedly, making it difficult to move materials between facilities. Power plants were targeted, leading to inconsistent electricity supply that affected heat treatment processes. Factories were damaged, forcing production to be moved to less suitable facilities. Skilled workers were conscripted into the military, replaced by forced laborers who lacked the training and often the motivation to maintain quality standards. The metallurgists in Makonen's laboratory were witnessing all of this, encoded in the structure of the steel samples they analyzed. Each batch of armor told a story. Early 1943 samples, excellent alloy content, perfect heat treatment, consistent quality. Mid-1943, still good, slight reduction in some alloying elements, but overall acceptable. Late 1943, noticeable decline in nickel and molybdenum, some inconsistency in heat treatment. Early 1944, significant reduction in alloy quality, evidence of rushed production. Late 1944, brittle steel, poor heat treatment, minimal alloying elements. The implications were profound. Soviet intelligence officers wanted to know what this meant for combat effectiveness. Could T-34s now penetrate Panther armor more easily? Should tactics be adjusted? The answers were nuanced. A late-war Panther was still a dangerous opponent. The basic design was sound, and even inferior steel arranged at clever angles was better than flat, thin armor. But the myth of invincibility was broken. The Panther was no longer the unstoppable monster it had seemed at Kursk. Makonin's team conducted ballistic tests to quantify the changes. They acquired Soviet tank guns and fired them at armor samples, mounted at combat angles. The early Panther armor performed impressively, often deflecting or shattering shells that should have penetrated. The late war samples were different. Shells that bounced off early armor now punched through. Worse, the inferior steel was prone to catastrophic cracking. When a shell hit late war Panther armor, even if it did not fully penetrate, it could create cracks that spread across the plate, weakening the entire section. There was another discovery that surprised the Soviet researchers. Some late-war Panther armor showed evidence of previous damage that had been poorly repaired. Cracked plates had been welded and sent back into service. Defective castings had been ground down and patched. The Germans were not just building Panthers with inferior materials, they were also recycling damaged components that should have been scrapped. This spoke to a level of desperation that the Soviet scientists found both encouraging and sobering. Encouraging because it meant Germany was clearly losing the industrial war, sobering because it showed how far a determined enemy would go, how many compromises they would accept to keep fighting. Even as their armor quality declined, German factories kept producing Panthers. Even as the steel grew weaker, crews kept taking these tanks into battle. The will to continue was unbroken, even as the means to continue effectively were crumbling. The Soviet research had practical applications beyond just intelligence gathering. Understanding the decline in German armor quality allowed Soviet designers to make informed decisions about their own tanks. The T-34 was being upgraded with an 85mm gun. Tests showed this gun could reliably penetrate late-war Panther armor at combat ranges. This was crucial information that affected production decisions and tactical doctrine. Soviet metallurgists also learned valuable lessons about industrial resilience. They saw how dependent high-quality armor production was on rare materials and stable manufacturing conditions. This influenced Soviet decisions about their own armor formulations. The T-34 used simpler steel that relied less on exotic alloying elements. It was not as sophisticated as early Panther armor, but it could be produced reliably and consistently. When you could build 5 T-34s for every Panther, and when late-war Panthers were not significantly better than T-34s, the advantage was clear. There was also a propaganda dimension to these findings. Soviet authorities were careful about how they used this information. On one hand, it was valuable to let soldiers know that late-war Panthers were more vulnerable than earlier models. This could boost morale and encourage more aggressive tactics. On the other hand, they did not want to underestimate the enemy or create complacency. The solution was to emphasize that German tanks could be defeated with proper tactics and determination, while still respecting them as dangerous opponents. Makonin and his colleagues continued their work throughout 1944 and into 1945. Each new batch of samples added to their understanding. They began to recognize patterns associated with different German factories. They could sometimes identify when a particular plate had been produced based on its metallurgical signature. They tracked the decline in quality across different manufacturers, noting that some facilities maintained better standards than others, even as overall quality fell. By early 1945, the Panthers being recovered from battlefields showed armor quality that would have been rejected as unacceptable just 2 years earlier. The steel was soft enough that it could be dented by weapons that should not have affected it. Welds were so poor that plates sometimes separated during combat. Heat treatment was so inconsistent that hardness values varied wildly across the same plate. The Panther was still a Panther in name and appearance, but the material science that had made it formidable was largely gone. There was a particular incident that Makonnen later recounted which illustrated the extent of the decline. In March of 1945, a Panther was captured nearly intact near Berlin. It was a late production model, factory fresh, barely used. The crew had abandoned it due to mechanical failure rather than combat damage. This gave Soviet engineers a rare opportunity to examine a complete, undamaged vehicle. When they cut into the armor for metallurgical analysis, they found steel so poor that Makonnen initially thought there must be some mistake. The hardness values were lower than some Soviet tank armor from earlier in the war. The alloy composition was barely better than structural steel. This was not armor steel in any meaningful sense. It was just thick steel plate, shaped like armor, hoping that geometry alone could provide protection. Tests of this captured Panther confirmed what the metallurgical analysis suggested. Soviet guns that had struggled against early Panthers could now penetrate from angles and distances that would have been impossible in 1943. The 76mm gun on the T-34, which had required careful aim and close range to defeat early Panther armor, could now punch through from typical combat distances. The 85mm gun on newer Soviet tanks could defeat late Panther armor almost casually, requiring little more precision than shooting at earlier German tanks like the Panzer IV. But here is where the story takes a more complex turn. Despite the declining armor quality, the Panther remained a deadly opponent. Why? Because armor was only one component of combat effectiveness. The Panther still had an excellent gun that could destroy Allied tanks at long range. It still had good optics that allowed German crews to spot and engage targets before being seen. It still had the tactical advantage of being used primarily in defensive operations where the crew could choose positions and wait for enemy attacks. A well-positioned Panther with a trained crew could still dominate a battlefield, even if its armor was not what it had been. Soviet tankers learned to be more selective in how they engaged Panthers. Frontal assaults were still dangerous, even against late war models, because the gun remained lethal. But flanking attacks became more viable because the side armor was thinner and the steel quality made it more likely to fail catastrophically. Combined arms tactics, using infantry and artillery to suppress Panther positions before tank engagement, became standard procedure. The Panther was no longer an invincible superweapon, but it was still a threat that demanded respect and careful tactics. The German response to the declining armor quality was complex. Some officers knew about the problems and tried to adjust tactics accordingly. Panthers were used more cautiously, kept further back, protected more carefully. Commanders who understood the vulnerabilities tried to use the tanks as long-range fire support rather than breakthrough vehicles. But many crews did not know their armor was inferior. They went into battle believing they had the same protection as earlier Panthers, and sometimes paid the price for that false confidence. There is a darker aspect to this story that must be addressed. The decline in Panther armor quality was not just about materials and industry. It was also about the human cost of total war. The factories producing inferior armor were staffed increasingly by forced laborers, prisoners of war, concentration camp inmates, people working under threat of violence if they did not meet production quotas. The sabotage and deliberate defects that sometimes appeared in late-war German equipment were acts of resistance by people who had every reason to want German defeat. When Soviet metallurgists found welds that seemed deliberately weakened or heat treatment that appeared intentionally botched, they were looking at evidence of this resistance. Some German and occupied country workers risked severe punishment to produce inferior equipment that might fail in combat. The declining quality of Panther armor was not just about resource scarcity. It was also about the moral and political collapse of the German system, reflected in steel that should have been strong, but was not. Makonen's final report on Panther armor metallurgy, completed in May of 1945 after Germany's surrender, was a comprehensive document that traced the entire arc of the Panther's armor development. It started with praise for the early model's excellent metallurgy, acknowledged the gradual decline as resources became scarce, and ended with clinical documentation of the nearly complete collapse of quality standards in the final months. The report was both a scientific document and a historical record of how industrial capacity shaped military outcomes. The insights gained from analyzing Panther armor influenced Soviet tank design for decades. Soviet engineers took away several lessons. First, simpler designs using more available materials were more sustainable in long conflicts. Second, industrial resilience mattered more than peak performance. Third, quantity could compensate for quality if the quality difference was not too large. These principles shaped Soviet military thinking throughout the Cold War. There was also a recognition that the German experience held warnings for the Soviet Union itself. What happened to Panther armor quality could happen to any nation that overextended itself, that fought a war longer than its industrial base could support, that made strategic decisions without considering material constraints. The samples of steel that Makonen's team analyzed were not just evidence of German defeat. They were cautionary tales about hubris, overreach, and the ultimate limitations of even the most sophisticated military technology. In the immediate post-war period, captured Panthers were studied intensively. The Soviets test-fired every weapon they had against Panther armor of different periods. They documented exactly how combat effectiveness changed as armor quality declined. This data went into training manuals, tactical guides, and design specifications for future Soviet tanks. Some of this information was shared with Western allies, though the Cold War limited how much cooperation occurred. The Americans and British conducted their own analyses of captured Panthers and reached similar conclusions about the decline in armor quality. The story of Soviet metallurgists analyzing Panther armor is ultimately a story about how wars are won. It is not just about courage or tactics or leadership, though all of those matter. It is about industrial capacity, resource availability, material science, and the ability to sustain production under pressure. The early Panther, with its excellent armor steel, represented what Germany could do with full access to global resources and undamaged industry. The late Panther, with its inferior steel, represented what Germany was reduced to when cut off from resources and under constant bombardment. For the Soviet scientists who documented this decline, there was both satisfaction and sadness. Satisfaction because their work contributed to understanding and ultimately defeating a dangerous enemy. Sadness because they were looking at the failure of another nation's industry, another nation's workers, another nation's engineers, people who in different circumstances might have been colleagues rather than enemies. The microscope was impartial, the data was objective, but the men analyzing it were human, and they understood the suffering that the numbers represented. Sergei Makonin continued working in metallurgy after the war, applying his expertise to civilian applications. But he never forgot the Panther armor samples that revealed so much about war, industry, and human limitations. In later years, when asked about his wartime work, he would speak not about triumph, but about lessons learned. The best steel in the world could not save a nation that had overextended itself. The most sophisticated metallurgy could not compensate for strategic errors. And in the end, no matter how advanced your armor, if you could not sustain the industry that produced it, you would lose. The samples of Panther armor that Makonen's team analyzed are now museum pieces, preserved as historical artifacts. Some are displayed in military museums, cross-sections showing the internal structure to visitors who may not fully understand what they are seeing. These pieces of steel, cut and polished and labeled, are more than just old tank armor. They are physical records of a crucial turning point in the war, evidence of how industrial failure can undermine military success, reminders that wars are won in factories as much as on battlefields. Modern metallurgists who study these samples can see what Makkonen saw in 1944 and 45. The decline in grain structure quality, the reduced alloy content, the inconsistent heat treatment. The evidence of increasingly desperate attempts to maintain production despite lack of proper materials. These are professional observations now, historical data points. But when Makkonen and his colleagues first documented them, they were real-time intelligence about an ongoing war, information that could save lives and influence strategy. The legacy of this research extends beyond just World War II. The methods developed for analyzing enemy armor became standard procedure in subsequent conflicts. When Soviet forces encountered new Western tanks during the Cold War, they used the same analytical techniques Makkonen pioneered. When metallurgists worldwide study armor today, they build on foundations laid by researchers on all sides during the Second World War. Science advances through conflict, though we might wish it were otherwise. There is a final thought worth considering about this story. The German engineers who designed the Panther did brilliant work. The early armor was genuinely world-class, representing some of the best military metallurgy of the era. But brilliance at the engineering level could not overcome failure at the strategic level. Germany's decision to fight a war on multiple fronts, to take on enemies with vastly greater industrial capacity, meant that even their best designs would eventually fail. The Panther's armor declined not because German engineers became less skilled, but because they were asked to accomplish impossible tasks with insufficient resources. The Soviet metallurgists understood this. Their reports did not mock German engineering. They documented it carefully with professional respect for what had been achieved, even as they noted its decline. The samples told a story of resourcefulness in the face of impossible circumstances, of engineers trying to maintain quality even as everything around them collapsed, of workers doing what they could with what they had. It was easy to see only enemy equipment that became easier to defeat, but Makkonen and his colleagues also saw human beings struggling with the consequences of their leaders' decisions. In the decades since the war, the story of Panther armor quality decline has been studied by historians, engineers, and military analysts. It appears in textbooks on materials science as a case study in how industrial constraints affect product quality. It appears in military histories as an example of how logistical factors determine combat outcomes. It appears in strategic studies as a warning about overextension and resource management. The same pieces of steel that Makkonen analyzed are now teaching tools, their lessons applied far beyond the specific context of tank warfare in the 1940s. As we reach the end of this story, it is worth remembering that history is not just about the big decisions made by leaders in distant capitals. It is also about scientists in laboratories making careful measurements and drawing patient conclusions. It is about workers in factories trying to do their jobs under increasingly difficult conditions. It is about the intersection of technology, resources, strategy, and human capability. The Soviet metallurgists who analyzed German Panther armor were part of all of that. Their work helped win a war, advance the science of metallurgy, and left us with lessons that remain relevant today. The next time you see a preserved Panther tank in a museum, perhaps you will look at it differently. The armor that protected it, that made it formidable, that ultimately proved insufficient, is not just metal. It is history, captured in crystalline structure and alloy composition. It is evidence of what nations can achieve and what they cannot. It is a reminder that even the strongest armor can fail, and that understanding why it fails can be as important as making it strong in the first place. The Soviet metallurgists knew this in 1943, when they first cut into Panther armor samples and began their patient investigation. We benefit from their knowledge today every time we consider the relationship between industrial capacity and military power, between materials science and strategic outcomes, between what we design and what we can actually build. This is the story of how careful scientific analysis revealed the slow collapse of German industrial power, one sample of armor steel at a time. It is a story about metallurgy and war, about careful observation and patient deduction, about how small details can reveal large truths. And it is a story that reminds us that victory comes not just from better weapons, but from the sustainable ability to produce and maintain those weapons over time. The Soviet metallurgists understood this as they peered through microscopes at German steel. Their insights helped win a war and continue to inform how we think about military technology, industrial capacity, and the true foundations of national power.